Alright, so this question asks, a positive charge distribution exists within a non-conducting sphere of radius r. So we have a non-conducting sphere of radius r, and it is non-conducting, so a positive charge distribution exists within this sphere. The volume charge density is not uniform but varies with the distance r from the center of the sphere according to the relationship charge density equals beta, which is a constant, 1 minus r over r for 0 to r, where beta is a positive constant and the charge density is 0 outside of the sphere. First question asks to find the total charge in the spherical region. So in order to find the total charge, we want to add up the charge of every single point in the sphere. So we're just going to integrate from 0 to r. So the total charge is equal to this from 0 to r. What are we going to integrate? If we take each small point along this radius and create a spherical surface, and then that infinitely small movement along this radius kind of creates this small thin layer of volume. And if we kind of add all of those layers together, we will get the whole sphere. Another way to write this is each small layer, kind of like an onion we're adding together, has a certain amount of charge. How much charge it has is equal to this charge density times the differential amount of volume. Now each differential amount of volume is going to be equal to the surface area of the distance from the center. Now the surface area of a sphere is 4 pi r squared, so this will be dr. So each change in volume is going to be 4 pi r squared times the change in the distance, and that's going to give us our total charge, our incremental amount of charge. So what we have is this. Now we know that rho is equal to this, so we need to write down r over r dq, but we know that dq is also equal to 4 pi r squared dr. So we need to integrate this. What we can do is first remove some of these constants. We can pull out this, beta 4 pi 0 r 1 minus r over r squared dr. And then I can, I'm not sure if this is technically the best way. This is what I can remember. I'm just going to distribute this r squared into this. That'll give me r squared minus r cubed over r. And then I'm just going to split this into two integrals. We can write r as a constant here, we can write it as this. So here, now we're just, this is 1/3 r cubed, and then we evaluate this from 0 to r. And this one is 1/4 r to the 4th. Evaluate this from 0 to r, minus 1 over r, and then this whole thing for beta pi. So I'll write this over here. If we just plug in big R for this will be R3 over 3. And then this will be R4 over 4. And then it'll be multiplied by the 1 over R. So this will just be R3. And this times 4 beta pi. So if we simplify this, 4 minus 3 is 1, so we just get R3 over 12 times 4 beta pi. Simplify this will be beta pi R3 over 3, and so this is equal to the charge in the sphere. So the next part is, in terms of beta r, small r, and big R, and fundamental constants, determine the magnitude of the electric field at a point, a distance r from the center of the spherical charge, either inside, outside, or at the surface. So this is where we use Gauss's law, where the electric flux is equal to the surface integral of the electric field times the an incremental amount of surface area, differential of A, or area. So within the sphere, electric field times the surface area will be 4 pi r squared. Again, that's the surface that we're looking at, will be equal to the charge enclosed. Now with the charge enclosed, if the r is smaller than big R, then not all the charge is going to be enclosed. We're going to integrate from 0 to small r instead of big R. So it's just the same thing, except this big R is small r. And so we can move this 4 pi r squared to this other side. The pi cancels out. The r squared reduces it to 1. And then this 4 divided by 4 on the side gives this. So beta r over 12. So this is if r to here. So that is if r is equal to r, if small r is equal to big R, then it's just the same thing. E 4 pi big R squared is equal to beta. Now we have all of the charge enclosed. Oh, I did forget the permittivity here. So I do need this permittivity right there. Permittivity here. And so again, these pi cancel out, this r cancels out. This is 12 here. So E is equal to beta r over 12. This. And then if r is greater than r, then it'll be the same thing. Because the charge enclosed, it'll just, this actually won't be the same thing. It'll be this equals to this. 3 epsilon 0. These go away. So this looks like this. And then find the value of r at what the electric field is at the maximum. So if you kind of look at this, the maximum is going to be when r is equal to big R, because big R is bigger than any radius within R, and then after it gets any bigger than that, then it starts going off by the square of the radius, and so the biggest is right here. So the maximum electric field is when small r is equal to big R. Maximum value of the electric field is equal to this.